Whenever we make a measurement in chemistry, we would like to know how good that number is, how good the value is. We do that by three criteria. We look at the uncertainty, the accuracy, and the precision of that measurement. And that's the topics we're going to discuss in this chapter. In any measurement that I make, there is always some uncertainty in the measurement, and that uncertainty is usually dependent on the instrument or the tool that is used for making the measurement. In other words, if I'm measuring mass, volume, or temperature. For example, if I look at measuring mass, if I look at this old type of balance, I can only measure this to the closest gram, so I can measure 6 grams. If I spend a little bit more money, I can buy a better balance and measure it to 1 decimal point to the right of the decimal, and I get 6.3 grams. A little bit more money, 6.34. Spend a lot more money, I can measure it to 3 digits to the right of the decimal point at 6.349 grams. And if I spend a lot more money, I can get 4 digits to the right of the decimal point. So scientists typically report their numbers with 1 uncertain digit. So if I were going to report this in an article, I'd write 6 grams. If I were going to report this in an article, I'd report 6.3492 grams. That last digit, the 2 down here, is actually the error, the uncertainty in the measurement. We typically say that that's plus or minus 2 is assumed. So let's consider reporting the mass of 6.3492 grams using the scale on the right. That last digit, the 2, is uncertain. So as a reader, I know that it might be 2, but it could also be a 3 or a 4, or it could be 1 or a 0. That is the uncertainty in that last measurement. This measurement, however, does have significant figures. It has 5 significant figures, which means I'm going to report even the uncertain digit down here. 1, 2, 3, 4, 5 digits in this measurement. If I'm measuring volume, I also have some degree of uncertainty, and it depends on what type of tool I'm using. Let's say I'm using a graduated cylinder, and I fill it up with some liquid, and then I look at the scale. If I look at the scale here, this is 20 milliliters, this is 21, this is 22. I typically make my measurement at the bottom of this meniscus, shown here a little bit more magnified. And so this one here is somewhere between 21 milliliters and 22 milliliters. So I'm going to estimate that last digit. That's going to be my uncertainty. So when I put this into my notebook, I'm going to write down 21 point, and then I'm going to do an estimate. I'm going to estimate that to be a little bit more than halfway between them, so I'm going to say 6. So I'm going to write down in my notebook 21.6. Whoever reads that notebook knows that that last digit is uncertain, the 6, because it's an estimate. And so I'm going to write down 21.6, but people will know it's 21.5 or 21.7. These measurements have 3 significant digits. So for any measurement, we need to include the uncertain last digit, and all these digits together are called significant digits. Let's talk about significant digits and how to determine them. If I were to look at a paper and look at a number that is written down, I need to determine which ones are significant so I can get the uncertainty, that last significant digit. We typically read numbers from left to right. And so here's a number, 0.000240030. Okay, and I don't have units down here, but let's assume it has some units to it. If I look at the significant digits, the numbers that are the leading zeros are never significant. So these numbers are not significant. Any of the leading zeros, they're just placeholders for this. Okay. Numbers that are significant are any non-zero numbers, for example, the 2, the 4, the 3, those are significant. Any captive zeros, that's a 0 between any non-zero digit, so this 0 is significant, and any trailing zeros. Okay, that is trailing zeros when they're to the right of the decimal point or when they're in scientific notation. So in this case, I look at this value as written here, expanded 1, 2, 3, 4, 5. I have 5 significant digits. This one is uncertain. If I were to report that number in scientific notation, I have to include all 5 of those digits. So 1, 2, 3, 4, 5 raised to the minus 4th power. And those are the 5 significant digits. Let's do a practice exercise where I've provided 7 different numbers. We're going to determine which of these digits are significant, and then I also have some comments over here to the right. So if I look at this first number here, 2.12, they're all non-zero, so those are all 3 are significant. If I look at the second number here, 4.500, I have 2 non-zero, and I have trailing zeros. Those trailing zeros are going to be significant. So those are not placeholders. Those zeros are significant. I have 4 significant figures. This last one down here is my uncertainty. If I look at this third example here, I can see I have 4 non-zero digits. Those are all significant, but I have 3 zeros here. Those are leading zeros. So those are just placeholders. They're not significant. So I have 4 significant figures. The fourth example here, I have 1 non-zero digit and I have 3 trailing. I'm going to have 3 significant digits, and these 3 are just placeholders. If I look at 500, you notice I don't have a decimal point here. So if I look at this one, I know I have at least 1 significant digit, but I don't know about these 2. In fact, I could have 1, 2, or 3. It's ambiguous. If I put a decimal point behind that 0, then it's not ambiguous anymore. These become trailing zeros because I have a 0 decimal point here. So I have 3. And finally, here is a 1 in scientific notation. I have a trailing 0 to the right of the decimal point, and so in this case I'm going to have 2. There's no ambiguity here. Let's do another exercise where I look at significant figures, and I'm actually going to correlate them with the tool used to make that measurement. So in this first case, I used a ruler, and I actually reported a value of 345.5 centimeters. In this case, this last digit here is my uncertainty, so I have 4 significant figures. If I use a balance and I report 0.0058 grams, these zeros out in front are actually leading zeros, so they're not significant. So in this case, I only have 2 significant figures, the 8 here being my uncertainty. If I have an odometer and I measure how far I've gone and I report 1205 kilometers, I'm going to have 4 significant figures. If I use a beaker and I report 250 milliliters, I don't know if that 0 is significant or not. So I don't know how many significant figures I actually have here. There's a little bit of ambiguity. So I either have 2 or 3. I'm not sure which of these 2 digits here is my uncertainty. If I use a different device to measure volume that has a smaller scale, I can report 250.0 milliliters. In this case, that 0 out here is my uncertainty. So in this case, all of these digits are going to be significant. So I'm going to have 4 significant figures. After I've made a measurement and written down a value, I often have to do some arithmetic to that number, either addition or subtraction or multiplication and division for the simplest arithmetic operations. When I do addition or subtraction, my answer cannot have more digits to the right of the decimal than any of my original numbers. I need to account for my uncertainty. When I do addition or subtraction, my units also have to be the same. So let's say I add two numbers together where I have 2 digits to the right of the decimal point on my first number and 3 digits to the right of the decimal point on my second number. When I add those together, I cannot include this last digit to the right of the decimal point in my answer. I need to round it. In this case, because it's so small, I'm going to round it down to the 3 here, so my answer will be 102.73. This is a common thing that happens when I use calculators, because when I do arithmetic on a calculator, I often get a lot of digits to the right of the decimal point, and I need to correct that for my uncertainty to account for the right number of significant figures. When I do multiplication and division, my final answer can contain only the smallest number of significant figures found in any of the original numbers. We don't worry about the decimal point in this case. Okay? So my first number here when I'm doing a multiplication is 1.4. That has 2 significant figures. The second number has 4 significant figures. My answer can only have 2 significant figures when doing either multiplication or division. So when I get my answer, I need to round it to 2 significant figures. In this case, I round it down to 11. Okay. So there must be some rules for rounding if it's not this simple here. And the next slide shows those rules. So here's some rules. I examine the first non-significant digit. So for example, here I have a number and I need to round it to 3 significant digits. So I go from left to right, I go 1, 2, 3, it's a 6. But is that going to be a 6 or a 7? I need to then look at the next digit, the first non-significant digit. If it's greater than 5, I round up. If it's less than 5, I round down. Okay? And that's easy. So in this case, the 6 here, my first non-significant digit, so this would be 1, 2, 3. This is not significant. So this one, I round up to 7. So it rounds up to 37.5. Okay? In some cases, if my first non-significant digit is actually equal to 5, then I need to check the second non-significant digit. I got to move over one more digit. If it's odd, okay, I round up. If it's even, I round down. It sounds like some unusual rules, but that's just what's been adapted in the sciences. Let's now look at some examples. I want to round the following numbers to 3 significant figures. Okay, so first let's start with the first one. I can see here my original number has 4 digits and I want to round it to 3 digits. So I look at the first non-significant digits. It's less than 5, so I'm going to round down to 2.12. In this number, I have 5 digits, but I need to look at the first non-significant digit. 1, 2, 3. Here's my first non-significant one. It's greater than 5, so I'm going to round the 3 up to 4. Here, I have 4 digits. My first non-significant digit is a 5. So if in this case, because it is 5, I'm going to round it up because there's no digits after it. In this one, I have 5 digits. My first insignificant digit is 5. So I need to look at the next digit, which is going to be 2. Because it is even, I'm going to actually round down to 7. In another example here, I have 5 digits in 24.751. I look at the first non-significant digit. It's a 5, so I got to look at the second one. In this case, it's odd, so I round it up to 24.8. These two are tricky. Okay. Let's now look at a number which only has digits to the right of the decimal point. In this case, I have 1, 2, 3, 4 digits. I'm going to look at the first non-significant digit, 1, 2, 3, 4. That would be 4. It's less than 5, so I round it down to 0.0674. What if I'm doing a number of different arithmetic operations on my numbers? To avoid rounding errors in a calculation, carry all the digits through the calculation, let your calculator do the work, and then correct the number of places in the final answer. For example, if I want to take 99.12444 and subtract 6.321, that's subtraction. I have 5 decimal points here and I have 3 decimal points here. I carry those through, get a new value. Now I'm going to divide 92.80344, my answer from doing the subtraction, divide it by my number here, 27.5256. I get this very big long number on my calculator. If I go up here in the top one doing the subtraction, I can only carry through 3 digits to the right of the decimal point. So total in my answer, I have 5 significant figures here in the top part of my division, and I have 6 down here on the denominator, so I can only carry through 5. So my final answer will only have 5 significant figures. My answer that I report is going to be 3.3715. When we make a measurement, we also often discuss accuracy and precision. Accuracy is the word we use to tell us how close we are to the true value of a given measurement. This true value is often known as the literature value, and so we compare our measured value to the true value, and that gives us a feeling for accuracy. Precision is how well a number of independent measurements agree with each other. So I'm making multiple measurements and looking at to find out how precise my measurements are. Let's look at 3 examples here. I have 2 students who measured values on a ruler. One got a 2, one got a 3. So if I look at those, they're close to the actual value. This is the value it was supposed to be. So on average, their team's results are pretty accurate. If now I have another team of students who also measure the values, and all 3 of them come up with 2.3, these students, they are very precise because all of their measurements tend to be the same, but they're not quite as accurate, okay? Their values are different than the true value. If I look at another group of students and they all measure the same value, so they're very precise, and that value happens to be what the true value is, they're also very accurate. Let's look at a real-world application in chemistry and look at the accuracy and precision of measurements. I have a copper ingot where I know its mass very accurately. It is 54.4418 grams. That's my true value. I'm going to use 3 different instruments to measure that mass, and I'm going to measure them 3 times with each instrument. So I take the double pan balance. I measure the mass once, I get 50 grams. A second time, I get 45 grams. A third time, I get 47 grams. And I take the average, I get 47 grams on average. So if I look at accuracy and precision, if I look at accuracy, my average is not very close to my actual value, so I have poor accuracy. Also, my individual measurements, they aren't very close to each other also, and so I have poor precision. If I use an electronic balance in class to measure those same copper ingot, I get 54.4, I get 54.6 the second time, and I get 54.2 the third time. On average, I get 54.4. So in this case, I get good accuracy, but my precision is fairly poor because I only have an uncertainty of 0.2 here, where in this actual measurement, I have a lot more digits to the right of the decimal point. So I finally use a very good balance, and I measure the mass 3 different times. I get an average of 54.418. And if I look at the accuracy and precision, I see that my value is actually very good, okay? And I'm also getting very good precision because these values are all very similar. Good precision and good accuracy.